My name is Differential, and I would like to report on problem number 11, which goes for select circle magnets. So first of all, if you have stack of the magnet, of cylindrical magnets, and this have some elasticities, and we have to investigate this, and is it possible to join both ends of the magnet stick? So we have in the end the minimum, what is the minimum ratio that we can take, and this is what so this is the ratio of resultant circle divided by the circle of one magnet. So first of all, what we want to understand that is what is the elasticity of the magnet stick. So if we get just the stick of the magnet, we'll just apply the force here, and we have something which we understand that there is the angles. What we're changing is actually the angles do not change equally. So, and this is our first observation. It's not evident that it's happening like that. And we have if we did analogy with the ends loaded, just the beam, as we know that the formula for beam is just dependencies depend on force, which is the linear dependencies. And for the linear dependencies, we have something. Okay, I have to excuse me, but because there is the plot here, I know this problem of projector that there is no plot here. I can hear it here. I can see it here, but there is no plot here. So we have linear dependence here. But the problem here, we have the curve. This is our theoretical prediction, interpolation, and we can measure the force here. We can measure the force here. This is our first point. We can change the angle here. We can get our second point. This is how we can get this line. So this is our experimental verification. And what is happening is actually, it's not linear dependencies. It's have something which is decreasing with force, which is. So going further, is it possible to make sufficient elastic joint to both ends to get the magnet stick? Okay, boom. If we get something with the magnet stick, which is if not enough magnets, it's not possible to do that. If we go further, we can actually get the stick, which is the actual circuit, which is the circuit. The problem is that there is also always these angles. There is this one is actually equals to 0. This one actually equals 0. So it's not angles is not equally. This is all time we have such form that is stable. Okay, it's n polygon. So this is what we want to investigate. So the problem is that we want to investigate that for this problem that always what we have n polygon, and there is no radius for n polygon. So we want to investigate, actually we want to minimize ratio of n polygon. And this is very important. So first of all, I want to understand why we cannot make this perfect circle if we get something just like that. So we have the perfect circle just here. We want to verify it even experimentally. So we want to verify it even experimentally. We did a very close precision model. We'll just put it up, and it's never collapsed. Okay, it's never collapsed. So we thought it's just about a small angle. It's a little bit unstable, but it's never will be stable. So it's always the stable form is always the n polygon. And we go further, we want to understand what is happening like that. And to do that, so we want to understand the fields, we want to understand the physics, what's happening here. So to do that, we will know that the one magnet is create some fields, which creates some fields which is around this magnet, and this magnet will, in this field, will have some energy. So if we have the energy of the system, we'll calculate it. By the variation principle, we can determine if the position is stable or not. So this is what we get. So we have the fields of this magnet. Okay, it's not like that, but it's schema. Donc we have the second magnet, and so this is the idea. But now the problem is how to determine these two energy. And to do that, we'll not use the magnetic dipole, which is not the best approximation. But to do that, we'll use the model which is called Gilbert model, and I'll explain because it's very interesting. So when we get the energy between two electron charges, actually we can get energy between two electron charges. We know it just equals like here, and we have for all the system, it's just the sum integrate for all the charges. But for magnets, actually, it was proven that we can do the same thing. we have the magnets, and we have the charge, which is okay, there is no magnetic monopole, because all these charges is like the dipole in the magnets. And so we can calculate, actually we can calculate the same thing. We have the same equation for all the system, and actually what we get now, actually we can calculate the energy of all the system of magnets. And it's very cool, but we have to verify it. We have to verify it. First of all, we can verify it by Maxwell equation, just a calculation, and the next one by experiment. So an advantage of this Gilbert model is that it's very fast in the time of calculation. We can do any possibility, we can do many possibilities, and it's really fast to calculate. So first one is Maxwell equation. We did simulation with a console and we verified it. And the second one, we did experimental verification of the model. So first one was just one magnet here, the second one here, here in the X. So we change this distance, and depending on this distance, actually what we measure the force, which is just here. This is the force, and this is E distance, Z. And next what we did, we know that the energy is integrate this distance. So we integrate this distance, and what we get at the end, we have the energy between magnets, like here. So as you can see, you see, but this is the experimental points. You have here the Gilbert model, which is just goes like that. And you have experimental model, our numerical simulation, which goes more closer, but okay, excuse me, but there is no much difference between the curve, and so it feels very well. And this is very interesting. Next one, we want to verify this change of this angle, and changing this angle, the same thing, but verify experimental of this. This is experimental points. We have the Gilbert model. We have this one. This is Gilbert model. We have the simulation. Okay, so now we verified this model, and now we verify this. First, next one, okay, it's possible to make the equilibrium of free magnets. It's not possible. But experimental, we verify it, and now we understand it theoretically. If we go for graphic plots, it's so hard to understand. We have the plots, which is just goes like this. Okay, I will just turn the screen, but you can see probably here, but no, I don't know. But there is the pause which just goes. I just really excuse me because I cannot do it better, just like there. So we have the plot which is just here. So this goes like this, and we have actually this is not the maximum, and we have unstable position. And so this position is never stable, and now we want to understand. So now we want to understand the radius definition. So if we define, okay, we want to minimize n polygon, and what is the n polygon? What is the radius of n polygon? For us, that is radius of n polygon. We take this one. Okay, there is many possibilities, but there is no care what radius we will take. So next one, what we get, and we want to study this. So first one, we will study the point of contact. The first one is very important. The point of contact is actually displaced, and so to do that, we will just choose. We will choose all the possibility, and then we will calculate the energy. We will calculate the energy. Excuse me, really excuse me. We have to calculate the energy. The energy curve goes like this, and so we have the optimum D, and this is what we get. D, the displacement. What we get here. This is displacement, and this is our experimental points. This is our model, and so we can predict actually this displacement for the n polygon. And go further, okay, now we want to talk just about geometry. How can we minimize the radius of the circuit, of the n polygon, the circuit of n polygon? So first one, we can change the number of boards, and okay. So this is what we get instability, which is so hard to explain. We have instability.
Can you turn off the lights?
I know.
Will help.
Can you help me? Just because there is no plot here. I know it is so hard. Excuse me. Please. Okay, I don't think so. We have the problem is that we have instability. If we change instability, we'll choose just a little bit position. It's just a problem of projection, actually. So we will change a little bit position. We'll change position a little bit, and we'll calculate the energy. And what we get, actually, we have here the stable position, and so it's stable. This is a curve like this. And what we get, we have local minimum, so this is the stable position. So now we can calculate if it's stable or not, different configuration of it. So now we want to study, we just verify experimentally. This is our curve, a theoretical curve. This is all these values will be stable, all these values will be unstable because the energy is positive. So what we have our experimental verification for this. Now we want to optimize what is the optimal setting for us. What is the optimal setting for us is actually that we have the number of words which is bigger. I have to finish. I just, excuse me, can I just answer why? Like 1 minute, because I just every time I have to explain the plots. Okay, so we can change the radius, we can change the number of words here, and actually, as you can see, we have to minimize it. As next one, we can change the number of magnets, we have to minimize it, and next one, we have to, if we change the thickness of the magnets, we have to also minimize it because the radius will increase with the magnets. So what we have, the theoretical best case, actually, if we just increase enormous, this is n polygon, this is the circuit, and okay, well, this is the 3 magnets position, and if we increase enormous, this one will increase the ratio enormously, so as you can see here, and if we get in the end that we need to define the magnetization. So for our experience, we're using a Neodymium magnetization with the magnetization which is we define, because it's very important to define magnetization. For each magnetization, we have different values, and this is our experimental limitation. So what we get for the 2 magnets, we have the curve like this, and I will just go for the conclusions. So this is I will go for the conclusion. So this is what we study. We will study n polygons because only n polygons is possible. For minimal ratio, we have to minimize all parameters, and our best result is just like that. It's with the 2% ratio. Thanks for your attention. Excuse me for that. You can't see all the plots and.
Hello everyone, thank you very much for your presentation. It's a bit sad that I really couldn't see much of your data, so perhaps we should have some time discussing them because I can't see how they validate your theory or anything. But apart from that, let's discuss what you did, okay, and we can further elaborate on that. So, okay, as usual, we have here the key points of your problem statement. So, to begin with, we must study in this problem elasticity. And then, in order to actually see what is elasticity, I'd like to even start talking about it. I really would like to have a definition, an actual definition of what you mean by something elastic, although you did show that the analogy fails, but what is elasticity for you? Is there a way to measure this in your structures? And then, okay, it's this time, all right. So, yeah, so is there any way you could model this about your global stability or local, or perhaps model it as springs, which are elastic or something like this. Now about the minimal ratio, the ratio of the big R from your radial cylinder. How can we even start to define this radius big R? I mean, is there a circle? Because you've shown us your data, you just have n polygons, so how do you define these radius? Okay, is it from your inscribed circle, subscribed circle? How do you define this? What is your radius after all? And then, okay, so we could further elaborate on that. Now, here's a very important point. You modeled the interaction between your magnets using Gilbert's model. And then one very good question is, why exactly did you do this? Because, okay, it's simpler, but is it fair enough? I mean, what are your hypotheses? Can you use it, like, just because you want to every time? And then, well, why not model it using perhaps the interaction between dipole, magnetic dipoles or something like that, magnetic field and the magnetic dipole? Is it really that more complicated? I'm not quite sure. Because, so I'd like to explain what's your validation of using Gilbert's model. Okay, so the dependence in the geometry, and here I talk about your magnet itself. I mean, you can vary big R, but did you vary small r? I mean, you didn't, small r is the radius of your magnet, cylinder magnet. Because as you didn't mention at all your magnet as a magnet, I mean, you model it as a charge, electric charge, so what's the influence of the magnet's geometry, so to say, I mean, the actual radius of your cylinder? How can you put this into your model if you really want to compare your model with your experimental data? All right, so nice. So, okay, we talked about this. Now, I'd like to actually know about the variational principle, as our friend mentioned. Maybe we can go further on that, because I really didn't get the idea. But I think it's interesting, but I'd like to further explore this. Okay, why not dipole interaction instead of Gilbert? Now, you didn't mention at all friction. I mean, is it really absolutely irrelevant? Because, well, if you know, you want to make your structure stable, perhaps. I mean, if you just glue your magnets, like with super glue, you're basically just increasing your friction coefficient like really high. So, well, maybe friction is quite important here. You didn't mention at all. And I'd like to know why, and if you can consider this. Okay, and about, you know, Earnshaw theorem, which states that you really can't have a equilibrium, a global equilibrium for electromagnetic fields. Like, so, well, does it tell you something about your problem specifically? And okay, and now one question about your numerical simulation, because you've shown us a very nice picture, but which data did you feed to your simulation? I'd like to go to that again. So yeah, unfortunately, I couldn't see your data too well to see if your data really matches your theoretical, but then we can go there and see this a little bit better, because I'd like to know about error evaluation and that kinds of things that I just wasn't able to see. But, all right. Okay. And about discussion, yeah, I already told too much. We can just go over these topics and we can just discuss on these topics again. And I think, yes, now we just perhaps we must see.
Yeah, can you go for asking the question and I'll answer?
Yeah, okay, nice. So, to start with,
yes.
Why Gilbert model?
Why? Yes, I will explain why it is. The problem with dipole moments that we all the close interaction, all the close, and if we calculate the energy, we have the distance which is smaller than around the thickness of the magnet,
yeah.
which will not works, and also it have some problem with the if rotation. It's just okay if for this position it will go.
Yes.
But if we have something within one magnet is rotates around another one,
anymore?
we cannot use the dipole model because it's half arrow. They have
Yeah.
limits for the dipole
Okay,
model.
you can make a multipole expansion. So dipole is just the first term.
So this is what we did. This is what we actually. This is the Gilbert model. It's actually very interesting for us. So it's it's very simple. It's the dipole model. So it's just dipole model, and we have for the dipole model many dipole models, and now we actually consider this rotation.
Okay, so how do you measure? How do you actually give some physical interpretation for your electric charge in your Gilbert model in order to actually make a connection with your actual magnets?
Yeah. I don't know if it's very interesting. We can talk about more about experience, but okay, I'll explain it. This is just very theoretically.
But did you do this? Did you have good results?
This is what again. I have the Gilbert model for the position of the charge for Gilbert model. This is my spec. Magnetization for magnet. This is my experience. This is my Gilbert model, and this is the simulation.
Okay.
So it's not, but it's with fit coefficients of the magnetization of the magnets.
That's nice. Now, I don't know. I think it shouldn't work that well. I mean, why does it work so well?
Because it's magnets.
Yes, but
So
you're treating it as electric charge. So it's
yes, this is the coolest thing. We can treat it because there is many electric charge. This is the coolest thing. We have the magnets. We have the magnets, and what we have in the magnetic interaction is actually it's just simple. We have the all magnetic interaction, and this is the dipole magnets. It's not the charge. And as you can mention, that we have about the instability of the electric charge.
Okay.
We have the theorem about instability of electric charge. We do not have electric charge.
Anyway, so about
magnetic charge.
Okay.
And this why we have the limits by geometry. The stability in
but why
geometry.
is
It's not the stability of all magnetic charge in the fields. It's stability in geometry.
So if you mentioned geometry, geometry here, how do you define your radius, the radius of your circle?
My radius of the circle,
Yeah.
I just define like that.
Because you really mentioned, well, they are polygons, so how do you define it?
Yes, I will explain it, no problem. I have this definition, which is just here. I'll go here.
Because you've shown us some irregular polygons, and then it's even more complicated, like you had the star.
This is my radius definition. Okay, go on further. This one.
Okay, but what about for the next result you showed us? Like for the star, you had like a star-shaped thing. When you displace, you make the displacement.
This one?
Yeah, I mean, yes.
Yeah, but this one was happening in real life. As you can see, in real life, there is no possibility, even with any type of magnets, there is always the displacement.
Yeah.
The displacement, as it's shown just here, displacement of magnet is just always
So,
there.
so thing is, in real life, you couldn't ever make
I can, but this position is more stable than in
Okay,
other one.
it's stable. Then how do you define your radius here in this position?
But the same. Okay. I
Yeah,
got it.
that's the point.
So with the same thing, it's actually what I got. This is the radius just between all the. Okay. Oh, alright. So this is the radius just in circuit here. So it goes for this point.
Okay. Okay, nice. Alright. Okay, so and that's a theoretical plot, right?
This is theoretical.
So later you shown us some.
Yes, this I show
Some data?
I show this is data for instrumental verification.
Yeah.
So I get this is unstable, and what we get, we get just change the geometry. So we change the air, what you call air with the magnet. This one. We change this one, and as you can see, we have the stable position, and then we cannot stable. We have a stable position.
Oh, okay. I see. All right, all right. Now about friction.
Yes.
Did you consider friction at all? Is it okay? Is it not important?
It's very question of yes, it's a very good question actually. But this is why I actually I have 30 seconds. Yes, this is why actually we have to define magnetization of the magnet. If we get magnet is just the metal which is a little bit magnetized, we can do whatever we want because the friction is very important. So what we consider the friction is negligible because if not, there is no problem in this subject. What we try to do, actually there is friction, and we wanted. It's not a problem to just take it into calculation.
But later on.
Thank you very much.
Hello everyone, my name is Olga, I'm from Team Ukraine, and today I'm going to review the problem number 11, circle magnet. In this problem we were asked to stick to join both ends of the magnet stick and find what is the minimal attainable ratio of the radius of the resulting circle of the magnet to the single magnet radius. Starting with the overview of the report, the reporter firstly performed a clear explanation on what is the elasticity of the stick, and it was very good. We saw a good demonstration. Then the reporter demonstrated us polygonal structure, and we saw what the reporter did in his experiments. Then the reporter discussed the magnetic field modeling using dipole approximation and find out that we need to use another model, Gilbert model, and finally perform stability analysis in order to find which shapes are stable and which are not. However, the reporter didn't show us precise field simulation for a lot of magnets that he said he performed, and it would be interesting to see it. Also, the reporter didn't, in his report, he didn't said anything about friction, and it would be better if he did. And also, unfortunately, he had some technical problems. So we believe that work performed on a good level, but needs further investigations, and some points should be clarified. About the opponent work, opponent asked about applicability of Gilbert model firstly, then he asked why the dipole approximation is not used. However, it was answered in the report, and it was weakness of the opponent opposition, and then he asked about geometry consideration and pointed out on the importance of friction forces in the system. About the discussion, the opponent unfortunately firstly discussed the dipole approximation, and as I already said, it was in the report, and it wasn't very fruitful to discuss this point because we already saw that it is not applicable in our problem. Also, then they discussed stability analysis, which was very good, and role of friction, and we saw that a reporter said that friction with surface is fixed and wasn't taken into account, which should be somehow clarifies on the polemics. And I propose you to discuss influence of the magnetization of the magnets, which is better to take as a strong magnet, the high magnetization or weak magnetization. And let's start the discussion with this point. First, the reporter and then the opponent, please give your opinion on this topic.
Go further. So first one, I'll go for this question. So we have. I will just define what we have. We have this one, and we have strong and small magnets. So for the problem is, for example, this one. So the problem is with the strong magnets is if we have the strong magnets, we have the friction force of the table, which is very important. And I just will mention that I didn't calculate the friction force here, and I said that this friction force is enough to just this is the criterion of the collapsing, actually. But this is criteria of collapsing is actually folding on this collapsing all the system, and this is what I calculate.
Yeah, I understand.
And
Do you agree with this point? So do you agree with this?
Yeah, I think it must be taken into account, sure. But the thing is, I can't really understand is because we do have a very powerful theorem which states that it's impossible to have a stable minimum with just electromagnetic fields. And you've shown us some plots and you've shown us some experimental data telling the total opposite. Like you have some graphs in which we can really see a global minima, like a stable minima, and how could you actually obtain that?
No problem. I will explain. So go for this term. If I will write that, I will do. So we have some. If we, we have this position. We have this position. We have this box which charge Q, and we have this box which which charge plus Q, and we have this box with charge plus Q. Is it stable? If it was stable, there is friction coefficient, there is many coefficient. The problem with the magnetization, there is no charges. There is no magnetic charges. It's just many dipoles.
Yeah.
This is the same thing. We have the magnetic. It's not just dipole approximation. We have many dipoles like that. And we calculate with this dipoles all the parameters. We just calculate the same thing as you propose. Just why we didn't take the dipole model. This is the dipole model, but we go further and we take there is many of dipoles.
Yeah, I think it's clear now, and I want to hear your point on the magnetization. Is it better to take the magnets with strong magnetization or with weak magnetization?
Better is a strong word. I mean, it's a parameter. It's a very important parameter which I think you should vary in order to see if your ratio varies. And I agree. Okay, it's a input. You have your magnetization. You have a different ratio. But then I don't know. I think you didn't vary this.
I would just answer. So
you just choose to have weak magnets.
Which is very logical. If we have the magnetization, if we have small magnetization,
in order to minimize it. Okay.
Yes, this we have small.
I agree.
Yeah,
sure.
And we have small magnetization. What happens? This is just the metal which magnetizes. We
Agree.
just go for on the table, and it will be
I
stable.
think it is clear now.
So
it's clear.
We just clear that this position is more is preferable.
Okay, and let's discuss the point. I want you ask to answer on the question: what is more efficient, increase number of edges or reduce radial ratio? So
What is it ratio?
Radial ratio.
What does it mean?
Of the magnets.
Of the magnets.
Yeah.
Okay, but increase number of edges as
So
I would prove it.
you had a number of magnets, and it is a number. Yeah, you had some magnets here, for example, 3, and is it better to decrease this number of magnets or decrease this length of the magnet?
Got it. Okay, it's also it depends on what is the constant. What is the constant of the magnet?
So actually,
but for actual life, it's better to decrease the number of the magnets than the ratio.
number of the magnets. And what do you think?
Yeah, I agree.
You agree?
Yeah.
Okay. And now it is a team polemics, and I propose some team to bring the new point. Okay.
For the reporter, please. I think you got the point that it's really impossible to have a stable equilibrium just with electromagnetic force by Earnshaw's theorem, right? So they consider the friction and the contact force between the cylinder magnets, right? In our calculation. So you showed plots with a variation of your functional, of your energy functional that has a true minimum.
Yes.
It has a stable equilibrium.
Yes.
But it's impossible. So how can you connect this kind of thing of your experiment with this theory?
I think I just explained just here. Can you precise what wasn't clear? I precise here that we have equilibrium even with the charge. If we have force, we can get equilibrium because it's equilibrium in geometry. It's not equilibrium.
Just electromagnetic force.
Yes.
You have to consider normal forces of contact forces, friction forces.
Yes.
You have this equilibrium. So this expression. This
Yes. I get it. Okay. So yes, but I did consider the friction force. I just didn't consider verification around friction force. This is the criteria of instability. So I said what I said. We have here criterion of this is stable. It's collapsing either like that, and so it's collapsing either like that. So its point is not moving. Or it's collapsing just like that, so its point is moving. So I just have to calculate the criterion here of stability. So I didn't consider the variation around because of the friction force. But if I have this stable position, it's collapsing because the friction force is not enough. So I did consider this one. I didn't consider variation around some surface.
So that variational energy that you showed us in the plots,
Yes?
we're considering all of these effects.
No, not all of them. I know what does it mean, all of them.
Friction, contact forces, electromagnetic
Electromagnetic forces, yes, because we calculate energy. If a contact force, it was just the criterion of instability. Another one?
Thank you very much.
Yes, no
Let's
problem.
move on to the next point from the reviewer team.
I understood correctly that you define the radius of structure in such a way that the smaller number of magnets we took, the smaller radius of structure we obtain, and so the circle with the smaller radius is a triangle.
Yes, but we can define it other way. If we get the same, we did the same calculation for the radius, which just goes around the circle, it just goes here. And it would be the same minimum. Why? I can explain for you because we have this ratio plus distance of the magnets. So all the ratio that you can define is the same ratio because this is this circuit plus something of the geometry.
Okay, the point from the one.
I didn't get the connection between the radius of the cylinder magnet to the concept of elasticity that you showed at the beginning of the presentation. What's the influence of the radius of the cylinder magnet with the elasticity constant that you found, that you discussed? What's the connection?
What is connection between magnets and?
Yeah. Between the radius of the cylinder magnet, right?
Yeah.
With the concept of stability and elasticity that you showed us in the beginning of the presentation.
Also, the same thing. We have these magnets. I didn't actually get the
For
question.
example, if you
I
vary
know.
the size of the cylinder of the magnet,
Yes.
it would be more stable, less stable. How would this behave in
If we
function?
change what?
The size of the cylinder.
Yes.
Like
The radius of
yeah,
the cylinder.
yeah,
The
the
small
radius.
Wait, we did change it.
No, okay, but what's the relation with the elasticity?
With the elasticity.
Yeah.
What's the
Okay, I get it, yes. So this is, yes, if we go for the elasticity, it's actually, this is the, elasticity is parameter. Elasticity is parameter to talk about this beam, yes? I get it right. So if I talk without this beam, and you will talk about if we change here, if for model Young, which is constant, if we'll just take this distance, will vary this distance. Okay, we did this analogy. If you want, we can discuss.
Okay, thank you very much.
Okay.
And it's like last point from the reviewer team.
Okay, as I understand, you investigated some distance on which magnets may be shifted to get the equilibrium position.
Yes, this one.
Does this value depends on different parameters of the system or it's constant?
No, it's dependent with different parameters of system.
Here you investigated how it depends.
Yeah, yes, we tried to investigate it experimental. We verified that with two plots, we changed the different with distance. This one of them. So we just so this is one. What we get. So it's changing with R, the size of the magnets. Just size of the magnets and thickness of the magnets.
Okay, thank you very much. So we're going to finish with the concluding remarks by the report.
Okay, thanks for your attention. All excuse me for that my plots didn't work. It's I'll just go for the thickness more grand, more bigger. First, I will just do summary for the discussion what we discussed. So first of all, about this position, I think I was clear that we have no charge on the magnets. This position is just with very like that. So with very geometry, will not vary position of the magnets. Position of the dipole in the magnets is defined. We change the geometry.
Yeah, one short question is you just mentioned that every object has a magnetization. Is that really true?
Well, it's not really true. Okay, most you can find the object with magnetization, which is absolute zero. It's metal. We take the metal in ground. We take it, and there will be some magnetization.
And my second question is, I guess your support where you put your magnet is kind of a non-magnetic material, right?
Yes,
So
actually.
imagine that you use the side or the wall from the fridge, which is magnetic.
Yeah.
So will be, I mean, there will be impact of your magnet, of your magnetic potential so what will be the difference if you change it somewhere?
Yes, I will explain. So if we have, I will yes. Is there more? So we have the magnet. I will just and this. So this is the surface. We have the magnet just here, and the problem is the same thing with the friction. We have the friction which is equals mu coefficient with the force which up here. So the same thing which is just here. But if this was force, before it was mg with mass of the magnets and g. Now it would be plus force of between this magnet and the surface, which we have the force inclusive. So when we get, we have increasing of stability.
Okay, are there any other questions? Hopefully they don't require the slides of the report too much. Dan, you have a question? So Daniel has a question. To the reporter?
To the reporter.
Kirilo?
Yes, no problem. I was wondering, can I do something for you?
It doesn't matter.
Yes.
It's okay.
I have a question about, you pointed out, this geometry and so on, but you realize that the key point here is that maybe the text of the problem is a little bit ambiguous. In the sense, it describes everything as the ratio of the radius of the cylinders and the radius of the circle, not really taking into account what is the aspect ratio of the cylinders. So could you maybe point out this aspect, which is...
So the ratio of cylinders is not actually the radius of cylinder. I didn't get. So
yes,
what is the question?
radius of the cylinders, obviously.
No, can
you have the cylinder at a certain aspect ratio.
Yes.
And this I think that this point
so you
is not really
excuse me, really. So we have this. What you think we have the ratio, just this one divided by this ratio. Okay, probably if we have this one, we have another problem. This is the problem
Yeah,
that we want to. Yes, actually this one. Yes, it's true. We didn't start it. I have slides if someone wants it.
Does anyone want slides? You've got 2 minutes, so maybe one person. Go on, Anastasia.
Scroll through.
C'est vrai ou pas?
Not okay. The most interesting part is the last slides about when you did manipulation with thickness, radius.
Okay. Oh yes.
Reducing
No problem.
everything.
So this one was just proof of the displacement, just the displacement. Okay. Now what we get with this is optimal setup, so we can change it.
Much lower. Okay. Yeah. Thanks.
Okay, we will, now we can change the number of reports, the same thing.
You can
plots.
do faster, right?
Yeah, okay, no problem. You can do faster. So we can change the thickness, the same thing, we have to minimize thickness, and each time this is what we use our model to calculate the equilibrium position. It's not just wrong. Okay, we're wrong. Okay, this is the ratio. So this is just,
part was interesting.
I was telling to you that actually there is, if we define like this the problem, there is no interest in to increase enormously a d, because if we have to rest something constant, and something constant for us is magnetization, because if we increase d, we can decrease magnetization and it will work. So we say that with the magnetization which define it, we have optimal d. There will be no more. This position is unstable. So this is what we get. So for optimal, so we have to define a magnetization. And we verify that our model works with this coefficient of qubit model, and this is coefficient for simulation. And now we can change d, so we can change this parameter, and what we get in the end, we have this one is stable. And this is, it wasn't stable, but we think it's about, wait, it's not a question.